Alright class, fireworks. You guys have all watched fireworks on 4th of July. Now what makes fireworks exciting? Do not tell me explosion. No. What makes them pretty? Colors, right? Fireworks have different colors. Now, have you ever thought about when you're watching the fireworks, where does the color come from? Do they add dyes to fireworks to make them have different colors? No. The colors come from metals. They come from elements. That's where the chemistry comes into play, which is kind of cool. Now, next time when you're watching fireworks, when you see a yellow fireworks, that's sodium. If you see a blue fireworks, there is copper in there. If you see a green fireworks, that's barium. If you see a red fireworks, that's calcium. So think about that. That fireworks, when you're the next time you're watching the fireworks, I want you to think about that. Oh, this is pretty because of chemistry. So now what that means is different elements, they emit different types of light. Now, I want to give you a very simplified overview of what is going on and why different elements do emit different lights. Now, here you have the nucleus, right? And when orbiting around the nucleus, we have electrons, right? We have electrons. Now, what I'm going to call this, I'm going to call this ground state. I'm going to call this over here excited state. What happens is that when you apply energy, and when you're doing fireworks, you kind of need some sort of energy to make it go, right? You need a spark. So when you apply energy, what happens is the electron gets the energy and jumps into the excited state. Now, is it going to stay there? It's not going to stay there. What happens is it comes back down. It comes back down. And when it comes back down, what happens is it emits light. And different light have different colors. Now, the way I look at it is kind of like pushing someone on a swing. If you push someone on a swing, first of all, you have to push them. So you're applying energy. They go up. Are they going to stay up? No. They're going to come back down. The same thing. The electron are going to get the energy, jump to the excited state. They're not going to stay there. They are going to come back. As they're coming back, they emit light, and then that's colored. Now, why does sodium emit yellow light, but copper emits blue light? What does that depend on? What that depends on this gap over here. The size of this gap will determine the color, okay? The size of this gap will determine the color. So if this gap, for example, is larger, you emit more bluish color. If this gap is smaller, then you're going to emit more reddish color. So it depends on this gap will determine what kind of color the elements would emit. Okay, now we're going to talk this chapter, we're going to talk a lot of light and a lot of physics equation, and I don't want you to get lost and understand why we're going to talk about light. We're going to talk about light a lot. And here's why we're going to talk about light. Because based on the light emitted by atoms, we can learn what an atom looks like. So based on the light emitted by these elements, we can study those. We can analyze the light emitted by them. And we can understand what an atom looks like. What is their structure. So far, so good. Okay, so this is why we are going to talk about light. Because by analyzing the light emitted by different elements, we are going to learn about their structure and know what they look like. One time I was teaching this class, and a physics professor told me, don't call it light, call it radiant energy. It's the same damn thing. radiant energy, but it sounds so much fancier if I say radiant energy. So next time, instead of telling someone, go and turn off the light, you can go, can you go and turn off the radiant energy? Sounds cool. So radiant energy or light. We have different types of light, okay? We have different types of light. And something I'm going to put up, which probably you have seen this before. Electromagnetic spectrum. Electromagnetic spectrum. And you probably have seen this before. It shows you different types of light. It shows you different types of light. Now, different types of light are, we have gamma ray, we have X-ray, we have UV, ultraviolet. What's after UV? If you know it, shout the answer, even though I can't hear you. It's visible. What's after visible is IR, infrared. After IR, infrared, is microwave. And the last one is radio. Okay, so far so good. Okay, now as we go from the radio going to gamma ray, what happens is that the energy increases. So we go from into increasing energy. All right, these are different types of light. So different types of light have different energy. I want you to realize that. Different types of light have different energy. You're good so far? Okay. Different types of light have different energy. Now, visible light. That you kind of know, right? And I want you to remember that visible light is when the wavelength is 400 to 750 nanometer. That's when we have visible light. So when you have about 400 to 750 wavelengths, that's where we have visible light. 400 is more bluish color and 750 is more reddish color. So far so good? Okay. Now let's talk about this a little bit. This is like an interesting thing to talk about. How many of you guys, your mom or your grandma says, don't use microwave, that's going to cause cancer? Or my mom calls me every day and tells me all the time that don't use cell phone, that's going to cause you cancer. And there's so many things out there nowadays that every day I wake up, there's something new that they say is going to cause cancer, right? It's like, now popcorn is going to cause cancer. It's like, not popcorn, I like popcorn. So you have to kind of think about it critically. And the way I look at it, again, different people might look at this differently. I go, okay, radio is what, our cell phone is, and this is a microwave. Radio and microwave have such a low energy. Visible light has a lot more energy than these two. So if I was going to get cancer from these two, I would definitely get cancer from visible light. So I have to kind of think about these things a little bit. Now, UV, if you go to the sun, they say that's bad for you. I'll buy it because it has high energy, right? Much higher energy than microwave and radio. X-ray, when you go to the dentist, when they put like a shield on you before they take X-ray, yeah. X-ray has a high energy. Gamma ray, I'm just saying the heck out of that, right? Yeah, these have high energy. I would buy it. But something that has such a low energy, I don't know. I have to think about it. That's fine. All right, so far so good. So what I want, the take-home message was that these are the different types of light, and different types of light have different energy. Now light has a wave characteristic. Light has wave characteristic. Now, what that means is, when you have a wave characteristic, that means you have a wavelength. You have a wavelength. Okay? And that means you have a frequency. So that means you have a wavelength and you have a frequency. Wavelength is lambda, okay? And this is the symbol for frequency. And the unit for wavelength is meters. And the frequency is 1/s. Okay? So far so good. So light has a wave characteristic, which means it has a wavelength and it has a frequency. Okay. Now I want you to already understand these wavelengths and frequency before we move on. So let me put something up for you. If you look at these two, okay, so light has a wave characteristic, it has a wavelength and it has a frequency. So the wavelength would be right here, the distance between 2 points, okay? And if you look at it, basically it's like a water wave. You've seen a water wave, like you see the ocean. That's what it exactly looks like. That's what we call it, a wave. It's a water wave. So for the distance between these 2 points is a wavelength. And the frequency would be basically the number of cycles per second. How many of these cycles do you have per second? That would be the frequency. Okay. Now, here's what I want you to do. I want you to tell someone next to you, and even if you have a roommate, whoever you can find right now next to you, do that. Which one has a higher wavelength, A or B? And which one has a higher frequency, A or B? Okay? Alright, tell me the answer. Which one is going to have a higher wavelength, A or B? What do you think? A, right? A has a higher wavelength because you have bigger waves. You have bigger waves, okay? Which one you have a higher frequency? That would be B because you have a smaller wave, but that means you have more of them, okay? So here you have a big wave, you have less of them. You have more, you have smaller wave, that means you have more of them. So what can you tell me about the relationship between wavelengths and frequency? What can you tell me about the relationship between these two? They are inversely proportional. If I have bigger wave, that means I cannot have as many of them. So I'm going to have a lower frequency. If I have a smaller wave, that means I can have more of them. So they are inversely proportional. So far so good. This is great because I feel like you already know our first equation. C is equal lambda times frequency. Lambda and frequency are inversely proportional. What is C? What C is speed of light. C is speed of light. Speed of light is a constant. 3.00 times 10 to the 8th is a constant. Okay. Now, this point we already said it was frequency, and this unit for frequency is 1/s. It's not hertz. The SI unit is 1/second. And this is lambda, and you know the unit for lambda is meters. Alright. Now, here's what I want you to do. And you notice, you can do this. What would be the unit for speed of light? What would be the unit for speed of light? I need you to learn the unit. It's a constant speed of light. What would be the unit for that? What do you think? Yeah, so if you look at it, here I have meters. Here I have meters times 1/second. And this have to equal this side, right? So the unit for speed of light would be meters per second. Meters per second. Okay. Yeah? This is our first equation. Speed of light is wavelengths times frequency. Put a little box around it. And you already knew that too. That wavelengths and frequency are inversely proportional. One goes up, the other one has to come down. Alright. Beautiful so far. Now let's go back to light. So what we have said so far is that light behaves like a wave. right? And if you behave like a wave, that means you have a lambda and you have a frequency. Then they did a lot more experiment. And what else they figured out was that after doing a lot of experiment, they figured out that light also behaves like a particle. Okay, also behaves like a particle. And here comes our next scientist. Our next scientist is Planck. I think Planck has a C. Alright, a physicist, of course, and he came up with the idea of quantized energy. So far, what scientists have learned is that light behaves like a wave, but also, after doing an experiment, they said maybe light also behaves like a particle. So what is this quantized energy? What is this quantized energy? Let me give you an example. What is quantized energy is. Okay. Let's say I have here a ramp, and this guy is going up a ramp. When you go up the ramp, you're going to go in a uniform motion. And let's say this guy is going up the stairs. My drawing is not very proportional, so this guy looks very tiny compared to the stairs. So imagine this like a normal sized person is going up the stairs. When you go up the stairs, how do you go up the stairs? You go quantized, you go stepwise, you go 1, 2, 3, 4. Can you go halfway? You can't go halfway, you just come back down. You can't just go up halfway. You have to have enough energy to go up to the next one, up to the next one, up to the next one. If you have enough energy just to go halfway, you just come back down. That's exactly what it is. Quantized energy. You need enough, and you need a discrete chunk of energy to get to the next level. Okay, so far so good. Okay, so this was our first equation, the speed of light. Our second equation is going to be energy is equal h times frequency. Okay, energy is equal h times frequency. Now let's go over what this is. E is energy, you know that's cool. And the unit for energy is, give me 1 second. The unit for energy is joules, okay? This one is frequency, you know frequency, the unit is 1 over S. Now this one right here, H, that's also a constant, is a Planck constant, okay? Is Planck constant. And this constant is 6.63 times 10 to the minus 34. What is the unit of this constant? I want you to learn to see units. What is the unit of this constant? What do you think? Yeah? Alright. So, it has to equal joules. Do you agree? Which means the second has to cancel out, and I have to have joules. So the only way to do that, it would be joules times second. You guys see that? Because if it's joules times seconds, and then frequency is 1 over S, then what would happen is that the seconds would cancel out, and I would end up with just joules. And that's what I want, because it has to end up with energy. So joules times second is the unit for Planck constant. So far so good. Okay, beautiful. So we have this light, it behaves like a wave, it behaves like a particle. We have this quantized energy. Now, so things are really good. Now the next scientist that contributed to this was, of course, Einstein. Okay, now he did a little experiment. An experiment that he did, he had a metal surface. And then what he would do, he would shine radiant energy. He would hit this with radiant energy. Okay, now when he did that, what it would happen is, and then an electron would be emitted. He would hit it with light, with energy, It will shine light to this. When you shine light to this, an electron is going to be emitted. Okay, but he had to add enough energy. You had a discrete amount of energy that you needed to add in order for electrons to be emitted. Okay, so far so good. And each energy packet is called a photon and behaves like a tiny particle. So you're shining energy, and then again, each energy packet is called a photon, and it behaves like a tiny particle. And then you have to hit it with a photon and enough of that to be able to emit the electron. Okay, now let's summarize again what we talked about. So what we said is that light behaves like a wave. Light behaves like a particle. And light has quantized energy. Again, and this Einstein experiment is exactly the same thing. You need amount of energy in order for that to emit. Okay, so, and now what if we put everything together? This is paved the way to understand what an atom looks like. Okay, and the next scientist is Bohr. And Bohr put it all together, and he came up with a Bohr model. And you have seen Bohr model before. I'm actually going to go to the next page to show you what a Bohr model is. So everything we've learned, it paved the way for Bohr to have his model, which is we have a nucleus, and then we have these energy levels around the nucleus, okay? We have this energy level around the nucleus. And this was kind of interesting. So what it says that when you have an electron, and if you hit this electron with light, if you strike it with light, okay, if you shine light to it, the electron will get enough energy to jump to the next energy level. Or if you add more energy, it will go to the 1 and then go to the 1. But here's the thing, quantized energy. You have to hit it with enough energy and to go to the next level. Can it go halfway? It can go halfway. It will just come back down. So you would have to hit it enough to go to the next level. If you don't give it enough energy, it will just come back down. So quantized energy. So far, so good. Okay. And again, like the swing we talked about, then it's not going to stay there, right? It's not going to stay there. It would come back down. Yeah? You guys are good so far? So this is the Bohr model. Light behaves like a wave, behaves like a particle. It has this quantized energy, and we came up with this Bohr model. There was one more thing that was puzzling the scientist. There was one more thing that was puzzling the scientist. So we have one more puzzle. And let me show you something. Now check this out. When you apply energy, the electrons get excited, they go to the higher energy level, they come back down. When they come back down, they emit light. Now, when they emit light, you could get two different types of spectrum. You could get a continuous spectrum, or you could get a line spectrum. So, I'm going to add energy to the electron. It's going to get energy, go to the high energy level. It's going to come back down. It's going to emit light. When I emit light, there's two types of the spectrum I can get. A continuous one. This is a continuous one. It looks like a rainbow, right? It's a pretty rainbow. That means all the wavelengths are emitted. Or I could get a line spectrum. This is a line spectrum. What does a line spectrum mean? The line spectrum means that only specific wavelengths are emitted. Only specific wavelengths are emitted. Not all the wavelengths are emitted. So far, so good. Okay. So only specific wavelengths are emitted. Not all the wavelengths are emitted. Now, let me show you who would produce a line spectrum. Now look over here. Sodium, hydrogen, calcium, magnesium, neon, all the elements, all the atoms, when they get excited, they emit line spectrum. And that was really interesting to the scientists. That yeah, all the elements, when they get excited, they get energy, they go to the higher energy level, they come back down, they emit light, they always are going to have line spectrum. Now, this is a spectrum for hydrogen. It doesn't matter where you are, it doesn't matter what you do, every time you excite a hydrogen atom, these are the lines you get. The same for all of them. Doesn't matter what you do, doesn't matter where you are, you have a sodium atom, you excite a sodium atom, you would get a line spectrum. These are the specific wavelengths that are going to be emitted. So that was very interesting to the scientists, and it was puzzling them that why every time we excite them, this is what we get. Now, the one that was really interesting to them was first to look at the hydrogen atom. And this was interesting because every time that you excite the hydrogen atom, what you are going to get 4 lines, okay, in a visible region. You're going to get 4 lines. So every time that you do this, you are going to get 4 lines. I'm actually going to go over those 4 lines with you because you're going to do a lab on that one. So the wavelengths is going to be 656 nanometer, 486 nanometer, 343 nanometer, 410 nanometer. Again, it doesn't matter what you do. Every time you excite a hydrogen atom, you're going to get 4 visible range color. One in red. This is blue greenish. 343 is like blue violet. And 410 is like a violet color. Every time you would get that. And you saw it over here. Every time you would get 4. Where is my hydrogen? Here's my hydrogen over here. You would get 4 lines every time. Every time you would get 4 lines. Now, why is that? What's going on here? How come every time I excite a hydrogen atom, I'm going to get 4 lines? What does this tell us? Well, our next scientist thought that this fit a very simple model. And it's funny how to physicists this is a simple model. That's beyond me. So he goes, this fits a simple model. I want to tell you what this is going to fit. And here's a model that he came up with. Here's our next equation. Energy is equal RH is one constant, times 1 over n final square minus 1 over n initial square. And the RH, okay, the RH is Rydberg constant. So energy is joules. Now this is 1. This is the RH. This is 1. 1 constant. This is a Rydberg constant. Okay. The Rydberg constant is 2.18 times 10 to the minus 18. One thing I forgot to do. Bad me. I forgot to put a minus here. So it's minus RH, and the RH is 2.18 times 10 to the minus 18. Okay, what's the unit? Joules, of course. Have to end up with joules. And n final minus n initial. We're going to go over this in a second. But he thought that, okay, what this means is this fits a very simple model. I was like, okay. Now, let's go over this simple model. So, I'm going to draw this out. Let's draw this out together. We're going to have the energy levels, okay? Here's my ground state. And I'm going to call it energy level 1. And then leave a lot of space. And then go to n equals 2. The spacing matters. It's not like I'm completely bad with drawing. And then n equals 3. And let's go just to 4 of them for now. N equals 4. The spacing matter. Okay. Now, remember the electron is here, right? The electron is there. An electron, when it gets enough energy, is going to go up to, that was a bad line, let's try it again. It's going to go up to the excited state. What we call that absorption. We call that absorption. So what we call that absorption. You guys are good? We call it absorption. And absorption has a positive energy because you need energy to make it happen. So it's a positive energy. Now we said it's not going to stay there. It's going to come back down, right? When it comes back down, we call it emission, right? It emits the light. And that has a negative energy. Okay? So that he came up with this. The spacing matters. Basically what it is, these are the allowed orbitals. Only specific frequency can be absorbed and emitted. And that's why we only get 4 lines. In a visible region, of course. So again, only specific frequency can be absorbed and emitted. And that's why we only get 4 lines. And the energy is basically minus RH over N square. This is the energy for each energy level. Okay? This is the energy for each energy level. So let's come over here. So if I'm on the first energy level, the energy would be what? Would be minus RH divided by 1. Because N is 1, 1 square is 1. If I go over here, it would be minus RH, which is 2.18 times 10 to the minus 18. That's the constant. Divided by 4. N is 2, square is 4. If I come over here, is minus RH over 9. Over here would be minus RH over 4 square would be 16. Okay. So what would happen is basically you do all this and you graph this. This is the graph that you get. If you do all this number, if you actually find this number and then you try to graph it, you graph this something like that. You'll see that between this and this, there's a huge gap. Between this and this is a little bit less of the gap. So if you actually put 2.18 times 10 to the minus 18 divided by 1, okay, then it will be 2.18 times 10 to the minus divided by 4, and keep going. If you have all this number and if you graph them, this is a graph that you would get. That between this one and this one is a huge gap, and the gap gets smaller as you keep going on. Okay, so far so good. All right, now let's go over this one more time. What they saw that every time you excite a hydrogen atom, you see 4 lines that never fails. Every time you do that, you get 4 lines, okay? Every time you do this, you get 4 lines. You go, okay, what does that mean? Why do we get 4 lines every time we see this? Then Rydberg's like, oh, that's easy. It fits a simple equation. I love it how they call it simple. And you're going to be amazed in about 10 minutes how right this equation is. Just wait. Now, what that means is, he said for every energy level, each energy level, the energy is minus RH over N square. Okay? So that means this is energy level, this is the second one. And if you graph this is the spacing that you get. What that means is only specific frequency can be absorbed and emitted, and that's why we get 4 lines. And what the other thing it means is that the spacing really matters. There is a fixed radius. So when we do, like, for example, this is a nucleus, the first energy level is going to be over here, right? So the spacing really matters. And that's my N1. This would be my N2. And then my N3 would have a smaller spacing than my N1. You guys get the point, right? This is my N1. Between N1 and N2, there's a huge spacing. And then between N2 to N3, less of this spacing. and it keeps going. So this orbital that we drew, the radius matters. It's not just right here, let's go by here, they're all the same size. That's not true. It's going to be, the spacing is going to matter. And this is like 1D of that. Yeah? Okay, so I think I got my point across that the spacing matters. Now, I want to do 2 practice problems to end this lecture. Before I do 2 practice problems, what we're going to do together, we are going to rewrite all the equation. Speed of light is wavelengths times frequency. Energy is equal Planck constant times frequency. And energy is equal minus RH times 1 over n final minus 1 over n initial. Okay? There is one more equation I want you to know, and that is combining these 2 equations. If you look at this is energy and frequency. This is wavelengths and frequency. What is missing is a relationship between energy and wavelengths. So it's kind of, again, you can just combine this together. It's always nice to have all the equation that you need in front of you. So here, if I combine these 2 equations, energy would equal hc over lambda. It's a good equation to know. All I did, just combine this together. So I have an equation for energy and wavelengths. Energy, wavelengths, energy, frequency, frequency, and wavelengths. And then here, energy and the energy levels. So far, so good. Okay. Ready for our first practice problem? What is the energy associated with 540 nanometers light? Pause me, do this, and then we're going to go over it together. So, I'm asking you for energy. And I give you nanometer. I give you light. Energy and wavelengths. I'm going to come over here. Which equation is that? Oh, our brand new equation. Energy and wavelengths that's the relationship between them. Okay, so what I'm going to do here, I'm going to say energy is equal hc over lambda. I'm going to plug it in. What is h? H is a Planck constant, 6.63 times 10 to the minus 34 joules times second. What was c? Speed of light, also a constant. Alright, now what's my wavelengths? You might say 540 nanometer. Except, remember, speed of light is meters per second. That's my constant. You always are limited to the unit of the constant. The constant will dictate your unit. The constant will dictate your unit. So this is meters, which means my light has to be meters. We said wavelengths has to be meters. If you want to plug in anything here, it has to be meters. What I have is nanometers. So I need to convert nanometers to meters. You guys got that down? So anytime you want to be able to cancel things out in this equation, it has to be meters. Nanometer comes down here. Meters goes on top. Yeah, you guys know that. So this can cancel out. The relationship, which one is a larger unit? Meters. 1 meters is 10 to the 9th nanometer. So what I end up getting is 5.14 times 10 to the minus 7 meters. I want to come over here, plug it in. Now, what I end up getting, do this, make sure you get the same answer as me. I get 3.87 times 10 to the minus 19 joules. That's what I ended up getting. So far, so good. Beautiful. Okay. Let's do our next practice problem. And our next practice problem is really good. It's going to bring everything home. You'll see. All right, let's do this. Here is our next problem. Okay, so calculate the wavelengths. So I'm asking you for wavelengths, okay? When an electron in a hydrogen atom goes from N3 to N2. Now, in this problem, the only thing they've given you are the energy levels, right? Now, the only equation that you know that has to do with energy levels is this one right here, the Rydberg equation. Do you agree? Again, remember, have the equations in front of you and then decide which equation you have to use. So the only thing that problem has given me are the energy level, so I have to use that equation. So far, so good. So energy is equal minus 2.18 times 10 to the minus 18, which is a constant for Rydberg, times N final minus N initial. Okay, so minus 2.18 times 10 to the minus 18. That's just a constant. What is my N final? So it says you go from 3 to 2. So my final is 2 square. That was a weird square. What is my initial? 3. Do you guys agree? Because based on this, what's happening is I am going from N3 to N2. So my final is 2. My initial is 3. So far, so good. Okay. All right. So now, if you plug this in, and actually get your calculator out and make sure you plug it in. If you plug it in, the number you're going to get is negative 3.03 times 10 to the minus 19 joules. What does the minus mean here? The minus doesn't really mean anything except it's telling me that this is emission. Because remember right here, I said when we go up, the absorption, the energy is going to be positive because positive means I require energy. And when you're coming down, you release that energy and that means the energy is going to be negative. So here, what I got a negative energy, which just means that this is emission. That's the only thing it means. Doesn't really have any other meaning except this is emission. So far, so good? Okay. Now, this is good. We found out how much energy is released when we go from N3 to N2. But that's not what the question asks you to. What the question is asking you to is what's the wavelengths. Now, let's come back to this one. Even before you had done the calculation and before you had put this in your calculator, you already knew this is going to be a negative energy because this is emission, right? When you go from a high to low, you're coming down is emission. So I could have predicted that is going to be negative energy anyway. So now the question asks you for wavelengths. What the question asks you for is for wavelengths, okay? So how am I going to figure out the wavelengths? I have the energy, I want wavelengths. What equation do I have? I have the energy, I need wavelengths. If you look at our little page, this is the equation I have to use. Energy equal hc over lambda. Because I have energy, I can figure out lambda. This is the equation that relates energy and wavelengths. This equation relates, so again, I need an equation that will relate energy and wavelengths together. That's this equation right here. You guys are good so far? Okay. Now, energy is going to equal, what is my h? H is a Planck constant, 6.63 times 10 to the minus 34. And then c is the speed of light, 3.00 times 10 to the 8th. Okay. Now, I don't have the lambda, I don't know what that is, but I have the energy. So I can put in the energy, which is 3.03 times 10 to the minus 19. You guys are following me so far? Okay. And I don't know why I just mushed everything together. So let's just do it over here. Okay. So again, let's go back over here. So I had the energy. These are constant. I have them. And I can figure out lambda. When I do this, again, you have to cross multiply it. It will be these two multiplied by each other divided by the energy. The number I end up getting is 6.56 times 10 to the minus 7. What is the unit? Tell me, what's the unit? The unit is meters. We talked about that. Every time you use this equation, speed of light is meters per second. So what I get out of this equation and what I can put in this equation is meters, except the question asks you for nanometers. That's no problem for you. You know how to convert nanometers to meters. So I have meters over here. Meters go down here. Nanometers goes on top. Which one is a larger unit? Meters. 1 meter is 10 to the 9th nanometers. 1 meter is 10 to the 9th nanometer. Okay, are we good so far? Okay, that's not bad. Good job so far. So now, what I'm gonna end up getting, and this is really, really cool. What you end up getting is 656 nanometer. 656 nanometer is my final answer. Alright, you're probably wondering, why the hell is she getting so excited? I will tell you in a second why I'm getting so excited. Before I tell you why I'm getting so excited, does the problem make sense? Let's go over it one more time. Every time they give you energy level and nothing else, there's only one equation you know that has energy level. So it makes your life easier. Plug it in that equation. You plug it in, you had the energy level, you get the energy. Okay? And the energy has a minus sign, which means emission. It doesn't mean anything else except this is emission. That's all he's telling me. But they didn't ask you for energy. They asked you for wavelengths. So I have energy. How can I get wavelengths? This equation relates energy and wavelengths together. And then I plugged it in. Probably you're sitting there and asking me, why did she forget to put the minus charge? I didn't forget to put the minus charge. Can I have negative wavelengths? I cannot. Like I said, the sign doesn't really have any numeric value. The only thing it's telling me is that this is emission. Okay, cool. I already knew it was emission anyway. So when I plug it in, I can just take the absolute value of it because I can never have a negative wavelengths. So far, so good? Okay. Now, before I tell you why this is the coolest thing ever, if you remember, we said visible light. Visible light is in what range? You have 400 to 750 nanometer is a visible light. 400 to 750. 400, it's bluish color. 750 is, oh, what did I write blue twice? Is, oh my god, I said one thing and I did something else. So forget what I just said. 400 is, no, don't forget. What I said was right. What I wrote down was wrong. So let's try this again since I confused the heck out of you. So visible range would be 400 nanometer to 750 nanometer. 750 nanometer at the end of the spectrum, that is my red light. At the beginning of the spectrum, the blue would be 400 nanometer. So is this within the visible range? Yes, it is. This is within the visible range. Now, why is this so cool? So when you plug in the number, this is the wavelengths you get, right? Let's go back over here. Yeah, 656, and it's red. Isn't that so cool? That Rydberg saw this and then came up with this equation. We just used this equation, and this is the wavelengths that we got. So when you go those energy level back and forth for hydrogen atom, these are the wavelengths that you got. 656, and exactly that's what we got. Pretty cool, right? So yeah, those numbers, they actually do correlate to this. Alright, so hopefully you got this down. Now, next time we're gonna finish this up next time. I feel like you've done a lot today. Now, before I let you go, this was great. Everyone was really excited about this because everything matches up perfectly. There was one problem. The problem was this beautiful equation only would work for a hydrogen atom. It would not work for anything else because a hydrogen atom has only one electron. When you put the second electrons in there, there's got to be a better model than this. Okay, I just had to leave you with that, and I will talk to you guys next time.